Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is Transformer Demagnetization. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as a moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Our presenter today is Ken Petroff, Power Transformer Product Manager. Also, to assist with the question and answer session, we will have two panelists joining us today, Dr. Diego Robolino, Business Development Director, and Vince Opedisano, Product Category Manager. Okay, let's go ahead and get started. Thanks for joining us today, Ken.
Thank you very much, Michael. My name is Ken Petroff. I am the Power Transformer Product Manager, and I am here today to talk about transformer demagnetization. So we have a few topics, and I do apologize because I just realized I pulled up the incorrect presentation, so just give me 2 shakes of a lamb's tail here, and I will get the proper one pulled up, because I had added a recap. And I do apologize for this slight delay here. I promise it will be fast. And if Michael, if you can just confirm that I am back up and running here.
We are in business.
Okay, fantastic. So apologies for that. But the topics that we are going to cover here today is, of course, transformer demagnetization. But we're going to start out by trying to understand why understanding magnetization is important. We will then look at what the effects of residual or remnant magnetization are. We will then get into some general theories of electromagnetism, how magnetism is handled by transformers. We will then look at the causes of residual magnetization in the transformer, methods for demagnetization, which will then include some demonstrations using the MWA and MTO and tracks from Megger. And then finally, we will recap on the topics that we covered here today. So why is understanding magnetization important? Well, transformers are electromechanical devices. They are the only asset in your system that actively converts electricity to magnetic fields and then back to electricity on the other side. So understanding magnetization is very important because it is the theory on which transformers operate. Magnetization what can lead to what is called residual or remnant magnetization. And why is it important and to understand the effects of residual or remnant magnetization? The first effect that remnant magnetization can have is on your protection scheme. If a transformer is magnetized and it is energized, you may have a false interpretation of adverse events on your protection scheme. Of course, this will lead to a power outage, and then there will be a lack of confidence in the assets on that system. If you are a tester or a test company, you will need to explain what happened, and oftentimes you will be the one taking blame first. And the first thing you're going to ask yourself is, did I do something wrong? Did I forget to demagnetize? What else could I have done wrong to cause this trip? More so, you're going to ask, did something fail? Both of these questions are going to lead to longer outage times to troubleshoot exactly what happened. The remnant magnetization, when it comes to this right here, the effect on your protection scheme, is definitely the greatest impact that it will have on you and your system. Of course, there is an effect on the transformer as well. This will lead to higher than normal inrush current, which of course can have the effect on the protection scheme as noted above. And more so, it can have unnecessary mechanical and electrical stresses on your transformer. And your transformer being, one of the most expensive assets in your system, of course, you don't want to cause any unnecessary mechanical or electrical stresses So making sure that your transformer is demagged and there is no residual or remnant magnetization is very important. If we look at other than the protection scheme and other than the transformer itself, there are effects of residual or remnant magnetization on your test measurements. One that people are probably most familiar with is the effect of excitation current measurements when you're doing your power factor testing. When you have residual or remnant magnetization, you will have higher excitation currents. When you're doing your SFRA sweep, you will also see higher readings. Most common, or where it's most pronounced, I should say, is on your open circuit tests, when you look at frequencies lower than 10 kilohertz. And what you will see is that your magnetized versus your demagnetized response will be higher. So that is one indication that your asset, your transformer, may be magnetized. You will also see a magnetic imbalance when you're doing a magnetic balance test. Magnetic balance testing is performed with a turns ratio instrument, but it can be another indicator that your asset is magnetized. So now that we have a good understanding of, why is understanding magnetization important and what are the effects, we'll go over some of the basic principles of magnetization and how these fields are created. Basically, current will induce a magnetic field. These magnetic field lines are drawn as lines, and they're actually closed loops. While you only see one closed loop here, each one of these loops extends out farther and farther, but for illustrative purposes, we just show the one closed loop here in the center. The higher the density of your magnetic field lines, the higher field strength you will have. And the magnetic field strength is denoted as H, or amps per meter. So a few properties of the coil. The number of turns will influence the magnetic field that you will generate. And then if we use Ampere's law, we look at the line integral of H over a closed field line loop, which is equal to the current enclosed by the loop. So if you are into math, we have this handy equation here that you can follow along with. But in layman's term, the H, or the magnetic field strength, is proportional to the current. So if you have more turns, you will have more current, which means you will have a higher or stronger magnetic field. In the real world, you're going to have a little bit different properties for uniform flux distribution, which is represented by this other equation here. Phi, looking at the flux density times the cross section of the core, which is that A sub C. And if we look at flux density, that is defined in terms of B, or Teslas, or Webers per meter squared. So lots of math. If you don't understand it, that's okay. We're just trying to go over some of the basics here. Which leads us into some more math. If we look at the flux density, this can be defined again as B, which is equal to the permeability, or that's mu, with permeability being the ability of material to accept a magnetic field, and mu sub zero is the permeability of free space. We multiply the permeability of free space by the combination of the magnetic field strength and the magnetization density. In a vacuum, the magnetization density happens to be 0. That is important because for a small m and a magnetic material with some mu sub r, which is a relative permeability, or the permeability of specific material, we can simplify this equation by saying that H plus M equals mu sub R times H, which then allows us to get rid of the M, and we can say that the flux density is equal to the permeability of free space multiplied by the relative permeability of the specific material multiplied by the magnetic field strength. So how does this work in an actual application? If we look at the total magnetic field strength plotted against the free magnetic field of a vacuum, which is mu sub r equals 1, and for this example, air can be considered a vacuum, which means that when a magnetic field is introduced into the vacuum or into air, the material in the air is not going to respond to that magnetic field, right? There are a few different materials. One is diamagnetic. This material will reject a magnetic field when it is applied. A classical example of a diamagnetic material would be a superconductor. When a superconductor is supercooled and a magnetic field is applied, it will reject almost all of the magnetic field, which is why you see superconductors floating around on that circle where they can be pushed along, because it is rejecting the entire magnetic field. Next, we have paramagnetic material. This material will accept a magnetic field. The important note with paramagnetic and diamagnetic material is that once the magnetic field is removed, it will lose the magnetism that it was introduced to it. This is in contrast with ferromagnetic material. Ferromagnetic material has a relative permeability much, much greater than 1. And I wanted to note that on this graph here, the relative permeability of the ferromagnetic material would result in a much steeper line. But for illustrative purposes here, it just should be noted that ferromagnetic material is relative permeability is much, much greater than paramagnetic, vacuum, or diamagnetic material. One interesting characteristic of ferromagnetic material is that after a certain point, no more magnetic field can be introduced because all the magnetic dipoles will become aligned. At this point, the ferromagnetic material will then act as a vacuum. In addition, the ferromagnetic material, once the magnetic field is removed, it will maintain or have some residual or remnant magnetization. So why do these different materials matter? Well, when we go to make a transformer, if we look at a transformer that's operating in air, similar to this, if we introduce current over here on the left-hand side, we will see that the second coil will receive a small magnetic field with very little current induced. And it's important for me to highlight here that what we are talking about is an ideal transformer, and it is a power or distribution transformer operating at 50 or 60 hertz. Of course, there are air transformers that are out there, but that is not the application that we're referring to today. So if we're talking about a power or distribution transformer, and we see that air will result in very little current induced in the other coil, how can the magnetic field be guided? We guide that magnetic field by introducing a core of ferromagnetic material. This ferromagnetic material will guide the vast majority of the magnetic fields from the first coil into the second coil. The magnetic field that is present in one coil versus the other is proportional to the current times the number of turns. So you will have the same magnetic flux through both coils. So the number of turns on the primary, and the number of turns on the secondary. You can look at two equations, whether you're talking about current or voltage, they will result in the same magnetic flux through both of the coils. Of course, if you want to get into more specifics, there is more math where we look at that phi, which we talk about magnetic flux or Webers, and then that can also be represented as volt-seconds. You look at the surface integral of the normal component of the magnetic flux density passing through that surface. But if we think about it in terms of volt-seconds, that means if voltage and time are monitored, we can determine the flux density of that transformer. So how does this relate to the testing and the normal everyday operation of this transformer? Now that we have our coils and we have our ferromagnetic core, how is this transformer going to behave when it's in service? So if we plot our flux density against our magnetic field strength, what we will see is that when we inject a current, it will magnetize the core. The way that this is going up in the positive direction, we're looking at either positive DC or the positive cycle of AC. At a high enough current, saturation of the transformer will occur. And if you remember back from the previous couple slides, the saturation means that no more magnetic field will be accepted and that this, the ferromagnetic material will then act as a vacuum. And at that point, the benefit of the ferromagnetic core is lost. So there's no point in injecting any more current, trying to induce any more magnetic field, because you will not get a benefit from that core, which will then look like this, like that graph from the other slide. When we remove that DC current, or the AC cycle turns down into the negative direction, the magnetic flux will decrease. Due to the ferromagnetic core, that decrease will follow a different path, and it will remain magnetized. This remaining magnetization is called remnants, or residual magnetization. If we continue to apply negative DC or let the AC cycle further down, we will get opposite magnetization again until we reach saturation on the negative side. The previous remnants is canceled at a certain H, as we see here crossing this line, and this is called the coercive force. The transformer must perform work to overcome this coercive force, and it is one source of loss in a transformer. If we start applying positive DC or let the AC positive cycle up again, we will of course get opposite magnetization until saturation occurs on that opposite side. It is important to note that remnants and coercive force points with opposite polarity are still passed. And this full B to H curve is called the hysteresis loop. Now this is if we're driving the transformer into saturation through every DC or AC cycle, which is not really how transformers are designed to operate. It may be how we test them. But the transformers are designed to operate within the linear portion of this hysteresis loop, and it's going to move along a much smaller hysteresis loop that is inscribed in that greater saturation hysteresis loop. It is important to note that this smaller hysteresis loop will still have remnants and coercive force points. So now that we've gone over some of the basics of how a transformer is going to operate under normal conditions, what are going to be some of the causes of core magnetization? We know that driving it up into saturation, letting it come back down, it will leave us with some remnants, but that really doesn't take into account of when you go to test or when you're looking at the transformer, why would it be magnetized? So if an asset needs to come out and you need to do some testing, you're going to shut down that transformer or that protection system, and it's going to shut that transformer down at a random point in its cycle. When it does this, it will come back down to a certain point and remain magnetized. Now that point could be here, it could be down here, could be up here. It all depends on when the transformer was taken out of service, and there's really no way of knowing where in its cycle it was. Another cause of core magnetization will be your winding resistance measurement. In a winding resistance measurement, DC voltage is applied to saturate the core, and then it is discharged. But after discharging, which takes the current back down to zero, the core will still remain magnetized. One of the other causes of core magnetization can be geomagnetic phenomena. One example of this would be, say, a solar flare. So we have three different examples of what can cause core magnetization. And it is our recommendation to always demagnetize your transformer. Whether you're going to put that transformer back into service or do testing, you should always magnetize. You don't know if there was any solar flares that came by that could have magnetized the transformer. You don't know what cycle or what part of the cycle the transformer was in when you took it out of service. And if it's a transformer that, say, has been sitting in your yard that is going to be put back into service sometime soon, you don't know what the last testing was done on that transformer. So you will want to demagnetize first before you perform any other measurements. And while that is Megger's recommendation, if you look at the standards, demagnetization is mentioned multiple times, whether you're doing an SFRA test, whether you're doing excitation current, and even when you're doing winding resistance, it will tell you that you have left the transformer magnetized. So Megger recommends doing demag first, and if you look at the standards, demagnetization is recommended all over the place. So to save yourself time, if you're going to do any other testing, always do demagnetization first. If you planned on doing winding resistance, you should consider doing that one before demag, but definitely demag before you plan on doing any excitation current testing, SFRA testing, or before you go to put that back into service. So now that we see that we should demagnetize, not just based on Megger standards, but also our Megger recommendations, but also based on the different standards that are out there, how can you demagnetize the core? Well, there is one method that is better than all of the rest, and this will involve injecting AC line voltage at frequency plus 20%. So 120% of AC line voltage. Typically, this is done on the middle leg of the transformer. And then what you're going to do is decrease the amplitude from saturation level down to zero with smaller and smaller loops for each cycle until the origin is reached. Now, 120% of AC line voltage is pretty expensive to generate. And if you're out there doing field work, it's not going to be very practical for you to do that. In addition to being impractical, if you are trying to do this as a field application, so outside of the transformer manufacturing location, it can be a relatively dangerous thing to do. So while it is the best, it is not something that you will typically perform when you're doing demagnetization in the field. For that, there is a standard method that is mentioned in some of these standards. Where you will inject the DC current that was used for the winding resistance measurement test. And what you're going to do is charge just until saturation, so just long enough volt seconds to reach saturation, and then you will discharge. After that, you are going to alternate polarity and decrease amplitude. And this is something that the Megger MTO and MWA do automatically, and with the Megger MTO 106, you can do manually. This will alternate polarity and decrease amplitude until you've reached a low enough point here where the transformer has been satisfactorily demagnetized. The pros of this method is that it's affordable. This is something that comes standard with these different instruments mentioned here. And it is practical since it is much lower voltage, much lower current than what you would do as opposed to the best method, which was done in the factory. The standard method, although will come with a few drawbacks, number one being that it is time consuming and it will leave the transformer with some remnants. You will not be able to get rid of all of it reliably. So there is another method of transformer demagnetization, which we will refer to as our best practice, which is called the adaptive method, and this is what is used in the tracks unit. If we look at voltage and time, if we measure those during the injection of current and discharge, the volt seconds gives us a knowledge of the flux density, and it can be used to determine the remnants that you started out with and the center point that you need to get back down to. I apologize if you hear some of my coworkers in the background. I have a 3-year-old son, and it's his nap time, and he is fighting it pretty hard. So anyways, getting back, if we look at volt seconds and the knowledge of the flux density to determine the remnants and center point, we will induce positive DC up to saturation, and then we will discharge while monitoring the volt seconds. From there, we will induce negative DC until the volt seconds of the negative start current is reached. So we will measure the time up to here and inject the same down here. And then we will discharge while monitoring the volt seconds there. We will then induce the positive DC cycle again, but only 50% of the volt seconds in the previous cycle. Again, we will discharge while monitoring the volt seconds, and we will repeat until the volt seconds reaches a reasonably low level. This results in a lower remnants and faster demagnetization. Now we will go over the different Megger instruments that feature demagnetization. Starting first, we have the MTO-106. This is our 6 amp winding resistance analyzer. It is a manual demag with the passive standard method where you charge and then discharge. It is not the adaptive method. We then have the MTO-210, 250, and MTO-3XX series. This will do the passive method, but automatically. So you do not need to monitor it. It will just automatically do the discharge for you. It is the same demag process that is found in the MWA 300, 330 series. The MWA, of course, being the multifunction tester for turns ratio and winding resistance. And then finally, the tracks, the multifunction transformer and substation tester, which has that automatic adaptive demag feature. So in the previous slide, I said that the adaptive demag was faster, but just how much faster is it compared to the MTO and the MTO-106? Well, in our Sweden factory, we have a couple of transformers. The first demag was performed on the smaller transformer. With the MTO-106, we can see that the remnants after the winding resistance measurement was at 1 amp. This value here and the remnants after demag were measured with the tracks. So the testing that was done to determine these values was a little bit of back and forth, since the MTO-106 and the MTO-210 do not measure remnants. But if we look at the MTO-106 here, the remnants after demagnetization was less than 10%, and the time needed for demagnetization was 3 minutes. So you can still do it. If you look at the MTO-210, you will see that it has the same level of remnants after demagnetization, but the time for demagnetization was cut in half. That is the benefit of doing that standard method automatically. And then finally, we have the tracks. Using that automatic adaptive method, we have a remnants after demagnetization of less than 1%, so a 10-fold improvement over the MTO-106 and 210, but look at those time savings. Much, much improved compared to the MTO-210 and 106. So that was on a relatively small transformer. If we go up to a larger one, a 20 MVA transformer, if we look at the MTO-106, remnants after demagnetization of less than 5%, and time needed for demagnetization at 8 minutes. If we go to the MTO-210, which does it automatically, same level of remnants after demagnetization, but we have improved our time by 2 minutes. And then the tracks. less than 1% remnants after demag, and it only took 42 seconds. So significant time savings when you are doing the demag with the tracks using that adaptive demag versus the passive of the MTO 210 and 106. As mentioned previously multiple times, doing demagnetization is extremely important. So even if you only have an MTO 106, you still want to do that demag before you perform any other tests or before you put that transformer back into service. However, with the tracks, you will find that that demag time takes a lot less. And now we have a couple demagnetization demonstrations. And this is where I'm going to invite Vince to talk us through the MWA demag, and then Diego through the tracks demag. Are you ready to go there, Vince?
I think so.
All right.
Well, first, when we select the instrument and we select our test form, we find that we can go right into a test, which is guided through a form. At this point, information that we would like to input is the basic information on the nameplate, which is voltage, kVA. And once that's done, the rated current is calculated. And when we apply a demag at this point, it will now know what currents that we should be applying. If you've already done a test, it will apply the test current that you've used for the winding resistance test. In this case, when we start, it starts at the negative amount of current that we've applied. So if we apply it on the positive side, it starts the current on the negative side. It runs through a charge, and then it runs through a discharge of that current. Now, this has all been highlighted quickly. And then once that's all been done and cycled through, it shows that the transformer has been demagnetized and is ready for other testing. And this is as simple as it is. If you start another test applying DC current, it will show this current, or show the demagnetize will go away because you've now applied and magnetized the transformer once again. It must go through demagnetize, and that's it. Simple as that.
Thank you very much, Vince. All right, and next we will look at the tracks demag. Are you ready for us, Diego?
I'm here.
All right, fantastic. Here we go.
Okay, so with our multifunctional tracks test set, as you can see in this example, what we're doing here is just running a winding resistance test. We've gone on the high voltage side, H1, H0, and we went from one tap to the next tap. Important, you saw the big screen saying that it's been discharging. And one thing that I really want to highlight is that discharging is completely different to demagnetizing the transformer. Now that you have the information, and you can see clearly here, you have the information of your transformer, you have the results from your winding resistance test. You can move into the demagnetization screen, and you can select, of course, that you are working from the high voltage side. That is our default condition. We're not working from the low voltage side. We go on the high voltage side, and we use the same current that was used for the winding resistance test. Meaning, if you applied, say, 5 amps to magnetize the core, you need the same 5 amps to demagnetize the core. And if you already have the results from your from your winding resistance test, you can use the information, the ohmic resistance information for this. With that being said, you just go now here, you have the information completed, and you will be applying the current right now, the DC field, into the central leg. That is by default. Now that we have a symmetrical distribution in the core, and you can see exactly what's happening. So we're looking for the maximum of saturation right now. We applied a positive signal. Now we're switching that to the opposite side. Once has maxima reached, now we're looking for the minima. We got to the negative point, And now we just go back and we start drawing the hysteresis of my transformer. And by doing this process continuously and changing the magnitude of the current that is being applied, we can locate exactly what is the point of zero remanence, zero coercivity, and that's where the process finishes. So it's a very simple, it's dedicated, it's adapted to the system that we're testing, and finally you get the result. You can see clearly the result. You have a plotted hysteresis, basically, of the process that you just carried out. You can look at the initial remanence in the core, and after the process, you can look at what was the final result. In this case, you have less than 1%. Very simple, very practical, and as you can see in this example, it took only 40 seconds to complete.
Thank you very much, Diego. So, a recap on what we talked about here today. Transformers are electrical mechanical devices. They're the only asset in your system that is going to convert that electrical to magnetic back to electrical energy, and that is the basis of why magnetization is important for you to understand. The ferromagnetic material will guide the majority of that magnetic field from one coil to the other, and that ferromagnetic material will remain magnetized when the field is removed. Magnetization can occur because the transformer was taken out of service. We don't know where in the cycle it was taken out, so we have to assume that there is some remnants still on that transformer. If you did your winding resistance magnetic test, you will leave the transformer in a magnetized state if you do not do demag afterwards. And then finally, your let's say your solar flares or your geomagnetic influence could also magnetize your transformer. And the big takeaway is that this residual magnetization can cause nuisance trips. This will lead to longer outage times. It will make you question, was the transformer demagnetized before I went to put it back into service? Or did something in my system fail? If you demagnetize the transformer, you can at least rule out one possibility, and it will allow you to reduce your outage time because you can focus your testing on other areas. But if your transformer is magnetized and you go to flip the switch and there's a trip, you're going to have lots of questions that you need to answer. In addition to your production system tripping adversely, your residual magnetization can influence test measurements. These can be used to evaluate the state of magnetization, whether it's through your excitation current test with your power factor test set, your open circuit SFRA, or magnetic balance through that TTR test. The main takeaway is to always demagnetize. Demagnetize before performing any test. Again, the state of the transformer magnetization is going to be unknown, and it's better to be safe than be sorry, so just always demagnetize your transformer before you start performing any tests. And always demagnetize before energizing the transformer. You want to eliminate those nuisance trips and provide confidence in your assets. And with that, we have, I'll turn it back over to Michael Fleischer, and he can discuss the survey and contact information, and we can go through any questions.
All right, thanks a lot, Ken. So at this time, the presentation portion of the webinar is officially concluded, and we'll take a few minutes to answer as many of your questions as possible. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote of any Megger products. A copy of this presentation, along with a link of the video recording of the webinar, will be emailed to everybody in about a week. You can also view recordings of previous webinars on our website at us.megger.com/webinars and register for next week's webinar, Cable Fault Location with Megger Smart Thumb Digiphone. The presenter will be Marshall Bird. All right, so let's jump into your questions. The first one I have is for Diego. Diego, does insulation resistance test magnetize the core?
Thank you, Michael. First of all, the short answer is no. When we're talking about insulation resistance, it's a completely different test as compared to a winding resistance test. Winding resistance, we're looking at the contact resistance or the static resistance that you will have on the winding. When you talk about insulation resistance, we're looking at the condition of the capacitive component of the system, which is the insulation itself. So there is a difference between a winding resistance test, which is an induced voltage test, versus an insulation resistance test, which is an applied voltage test. So again, the short answer is no.
All right, thanks. Next question is going to be for Vince. Vince, transformers are designed to withstand the inrush current. So why do you demag the transformer?
Yes, transformers are definitely designed to handle quite a bit of inrush current and are tested as such. The reason we want to demagnetize the transformer, and I, in fact, I have an old colleague from Hydro One who used to say, why does everyone care? We used to just turn them back on all the time. Well, in today's state with power, every time we get a magnetized state, it has the potential to trip a relay, which indicates that there may be an issue with the transformer. It may not. It may be unrelated to the fact that it's magnetized, but if we demagnetize the transformer properly, that chance of a mistrip from that relay is minimized to near zero, and therefore we can determine that a mistrip is problematic of something other than leaving the transformer magnetized. So we're not worried about necessarily the transformer and it handling the inrush current. We are more concerned with removing what questions may be asked when a transformer protective relay, like a differential, trips. Hopefully that answers your question.
All right, thank you. Next question is going to be for Diego. Diego, does the results from WRM change polarity to accurate results?
Okay, when you apply, say, a positive DC or negative DC, that is one thing. But I think the question is mainly oriented when you're doing a winding resistance measurement. If you go from on one phase, one direction, and then you go on a different phase in a different direction, how this will affect the measurement itself. So the more energy you spend, the longer is the time that you will be running the test. The idea is, of course, to follow the same orientation that you have given on the first test or the first phase that you have magnetized or saturated for the winding resistance measurement. That way, the next time, because you need the core to be magnetized, if you keep the same orientation of the magnetic system, right? Then you don't need more energy to move this to reorient the magnetic domains to a different direction. So if you keep this direction, one direction during your testing for all the magnetic system, then that is a more efficient process.
All right, excellent. Ken, the next question is going to be for you. Are there limitations to sizes of transformers that can be demagnetized with the MTO or MWA units?
So when we talk about driving the transformer to saturation, we're looking at volt seconds and we're looking at current. So of course the MTO units have certain voltage and current capabilities, and it will just end up taking longer. So what I'm going to bring back up here is this slide. So yes, you can demagnetize pretty much every transformer, but it's just going to take longer and longer to do that because when we look at the volt seconds, To get that up to 100% to charge it to saturation and then back down the other way, it's just going to take a longer and longer time. And that was also shown here when we look at this 20 MVA. And so as the transformers get larger, it will take longer and longer. But yes, you will still be able to demagnetize those transformers.
All right, thank you. Next question is going to be for Vince. How long does a transformer stay magnetized once it has occurred? Does it eventually demagnetize itself?
That's a very good question in that we are always wondering when we come up to a transformer, if it's been a year or two, and especially for spare transformers, what state is it in? Has something created a condition in the transformer, one of them being magnetization? And I have tested a large transformer that had been tested previously 1 year before. And in that testing, we found that that transformer was fully magnetized. We were at a point where our excitation current had actually gone more than 2 times the expected. And so as such, once we demagnetized it, it was the only way we could get the excitation currents that we expected back to within measurable or expected levels. So yes, it does stay magnetized. And does it eventually demagnetize itself? Not by any method that I am aware of.
All right. Diego, the next question's for you. If we ground the transformer, how long should we wait to consider it demagnetized?
That is an interesting question. How long? As long as you want. Really, there's no mathematical correlation between grounding the transformer and the magnetic properties itself, as far as I know. So you can try, but why would I spend time grounding the transformer and waiting it to get demagnetized by grounding it when I can just apply a procedure that will take down the magnetization in a couple of minutes? So I will go with a practical procedure instead of just grounding.
Okay. So Vince, how many times do we demag the transformer?
I'm not quite clear as to what the question means, but what I can say is that I have demagnetized the same transformer so many times and magnetized it and we've never seen any state that has caused any issues in the transformer. We did so as a matter or as a practice, an exercise to determine how magnetized we could get a transformer and how quickly we could demagnetize it, like some of the results that you saw in the presentation. So we don't really have a number of times that we demagnetize it, as many times as we need to.
All right, thanks. So Ken, how do we demagnetize the XFMR at the site?
So to demagnetize the transformer at the site, let's say you're using the MTO 300 series, you will have your 6 leads connected to the transformer because that's how you were doing your winding resistance test. And I will just bring up the example here in the video. This is the example for the MWA, but it should be noted that the same demagnetization procedure is used for the MWA or the MTO. Here we are going to select our 3-phase turns ratio and winding resistance form. Once that form opens up, again, we will have entered our line to line and kVA, which will give us our rated current. We will then, of course, apply up to 10% of the rated current for our winding resistance measurement test. When we click this demag button that's available within the transformer test conditions of that 3-phase form, you will see that this window will pop up here. Your test current is going to be the same test current derived from the rated current calculation on the form. We always populate with the high center leg because that is what is recommended and that is what has been shown to be sufficient for demagging the transformer. You only have to do it on one leg. And then you will click the start button. And What it will do then is it will start driving the current into the negative direction because you were doing all of your tests into the positive current direction. And as soon as it reaches saturation, it starts to discharge, and then it will go through and it will cycle through all of the different values seen here on the left-hand side. It'll go to 6 amps, minus 3.5, 2 amps, minus 1, so on and so forth, until, as you see in this example, it gets all the way down to the bottom of 1 milliamp, at which point it will say that the demag was complete. And then on the form, as Vince noted previously, in the transformer test conditions, it prints it out in very bold letters with this check mark saying transformer demagnetized. So that is the demagnetization process for the MTO and MWA series through that automatic method.
All right, thanks. Vince, the next question is going to be over to you. During winding resistance measurement test on different taps, do we have to perform the demag on every tap, or just at the end of all the tests? Do we have to perform that demagnetization?
I think we lost Vince for a second.
Sorry,
Yeah,
I was
it
on.
does feel like that.
I
Oh, there we
apologize.
are.
I apologize. Sorry. So on a transformer, when we're going through taps, we do not have to demagnetize. In fact, it's beneficial if we leave the transformer in its magnetized state, tap after tap after tap testing. And on energized tap changers, we leave the current on. We don't just discharge or such. We leave it on and we apply the next tap and we measure and we continue on. That saves us time. So there is no need to demagnetize while testing and winding resistance. And at the end, we can demagnetize if we're finished the winding resistance measurements. Sorry about that.
No worries. So while we have you here, the next question is also for you. Does it matter which polarity we start with in demagnetization in a winding or a transformer, where we place the positive, where do we place the positive and the negative leads?
Well, actually, the way the instruments are designed, we actually apply the test current, the demagnetization test current, in the opposite polarity because the transformer is already magnetized, let's say in the positive. So the next cycle in demagnetizing is to start with the negative. So you can reverse, it just adds more time and eventually you get to the zero state. So if somebody's doing it manually, they would reverse the leads to start demagnetizing, but in an automated state, the instrument does this for you. And if you want to start with positive demagnetization, you can. It's not really going to do anything because the transformer is magnetized in the positive direction. So hopefully that answers the question.
All right. So Diego, you can show demagnetization on the central leg, but should the other faces be demagnetized as well, or does the central leg leave the other cores demagnetized?
Okay, so different constructions of transformers, of course, and different the situations that you may have, but typically, let's if we look at the most typical construction on power transformers, which will be a core type design with 3 legs, you have 2 symmetrical faces on A and C, and the central leg representing the middle leg of the transformer. As I said, this is majority of the design that you may find outside. If that is the case, then the distribution that you have and applying a field to the central leg will have an equal distribution of the effect to the symmetrical faces and the parallel legs of your transformer. And one of the things that is most important for you to understand is, like we were saying during the presentation, you can demagnetize, yes. In the field, I don't think that you will be able to demagnetize as well as you can demagnetize in the factory, that's for sure, right? And most important is that you need to be able to take your transformer and demagnetize it to a point where it will not influence, right, on your protection scheme, and it will not create a big influence, of course, on your AC testing. So by demagnetizing it, right, and applying this this procedure, that's exactly what you need to do. And sometimes just demagnetizing the central leg is good enough. Interesting, of course, that you can run the demagnetization procedure and you can run additional testing afterwards, like magnetic imbalance, right? The magnetic imbalance test, which is also part of the characteristics of the different products. You can see if this transformer really went through this demagnetization process. So that's just a guideline.
All right. Vince, does demagnetization of the core affect inrush currents? If so, does it affect the relative strength of the second and fourth harmonics?
First of all, absolutely it affects the inrush current because the effective impedance of the transformer has been reduced when you magnetize the core. And accordingly, it affects the relative strength of the second, the fourth harmonics, which is where the relays are really designed to be sensitive to in tripping the transformer for possible faults.
All right, thanks. Also, for Vince, does shorting the winding lead help demagnetize the winding?
I think this question has been asked in a number of ways by different people. We think that there's energy in the winding, therefore if we short it, that all that energy dissipates across the winding by shorting, let's say H1 to H0 or H1 to H2, but this is not the case. What we're doing is we have a core which has got all of its steel oriented in one particular direction as opposed to in a neutral state. And therefore, shorting the winding does nothing but make us feel safer by shorting the lead, but it does nothing to help demagnetize or change the state of the core.
All right, thank you. Diego, what is the difference of demagnetization in factory and in the field?
Okay, that is of course a typical question that we get. And just imagine the circumstances you are working in the field. When you go to the field, you have a power transformer, different sizes, of course. You don't want to carry to the field lots of equipment. And one of the reasons why winding resistance measurement is a DC test and you need to reach saturation, it's because with DC, you can saturate the core with low voltage and low current. And remember that there's something that is important as well for you to understand. Flux is proportional to voltage. Okay, the voltage that you apply has a direct correlation with the flux. But if you look into the one of the mathematical slides that we had from Ken, you can see that it's not only Faraday's law that has been acting here. It's Faraday's law, it's Ampere's law, it's Lenz's law. All those physical phenomena are acting on the process. So when you do your winding resistance measurement, you are applying DC, and by applying this DC signal, you are getting into this saturation. Then you change polarity, you go into the negative side of the hysteresis, back and forth. But when you are in the factory, you have the ability to apply nominal voltage. In this case, saturation goes by over voltage, and you can play with other different magnitude of the electric field, okay? Or there's another method to play the demagnetization by changing the frequency on the AC signal. So that is the differences that we have between field and factory. Of course, you cannot bring a, I don't know, 100 kV, 200 kV, 300 kV AC source to do your demagnetization in the field. That would be kind of complicated. So better to go with a little piece of equipment, do your winding resistance, and use the same equipment to your demagnetization.
All right, thanks. Ken, demagnetization is said to be typically applied to the central leg. Would you like to expand upon that?
Well, I think Diego covered this before. And when you look at the typical transformer construction of a core type transformer, the magnetic field is shared amongst the outer legs. So if you demagnetize on that center leg, in effect, you will be demagnetizing the outer legs. Now, with a shell type transformer, it will be a little bit different. But for the vast majority of what you will be doing, demagnetizing on that center leg, since the two outer legs, share that same magnetic field, in effect, those will be demagnetized as well.
Thanks a lot, Ken. I think we have time for one last question before we have to wrap. Vince, DC testing can present some serious hazards to workers. Can you please speak to how your equipment is designed with that in mind?
Thank you. One thing before we get on to that question, I just want to elaborate just a little with Ken's explanation on that central leg of a core type. If you have a shell type transformer, which has 5 legs, not 3, what one can do and what one does to properly demagnetize it is connect the 2 outer phases in series and demagnetize the 2 at the same time. So if it's A and C, we apply in through A, out through C, and we demagnetize the 2 outer legs, and that is the best way to demagnetize a shell type transformer. Now, final answer, as far as serious testing, when I started long time ago, we did not perform winding resistance tests on transformers, not because of the dangers to the transformer, but more because of the dangers to the individuals, and more importantly, the equipment itself could not handle the sudden discharge of energy that was possible when you apply DC through a highly inductive specimen such as a transformer winding. And as such, if you are applying DC current to a transformer, understand that any removal of a lead while live is very dangerous to both yourself, is dangerous to the asset, not so much, but it still is not good, and as well to the equipment. And we, in the equipment, designed for this. So if you accidentally remove a lead, we have a safety path through our potential portion of the leads, which allows the transformer to safely discharge. But even when you do get a spark or an arc because you've removed it, the equipment is designed to safely discharge. It does so in a very quick way, but it can handle that inrush of energy, which is in the form of high voltage. Hopefully that answers the question.
All right, then. It does look like that's all the time we have for questions, unfortunately. We apologize if we didn't get your question today, but we'll try and follow up with you offline in the following weeks. But thank you all for attending. If you could please remember to fill out the survey and let us know how we did, we would really appreciate it. That survey will also include a field for you to request a demo or a quote if you're interested. I'd like to say once again, thank you all for attending and have a great weekend.
Thank you, everyone.